get started again. So we saw that the condition that a curve is integral to a vector field through a given point gives us a system of ODEs with smooth initial conditions, and therefore we see that the existence uniqueness theorem will give us the consequences that we desire. So I'll assume that we are familiar with this, the existence and uniqueness theorem for the solutions of systems of ODEs. Then gives us the following theorem. So you take a smooth vector field on an open set. So in Rn plus 1, smooth vector field. So you in Rn plus 1, and we take a point in U. Then there exists an interval I around 0 in R, and a unique curve. Why is the uniqueness in the curve? Because it's an initial value. So the condition that you require the curve to pass through the point. So this gives you the uniqueness. Yeah? So and the unique curve gamma. So notice from the system of equation, we are solving for everything at points on the curve, right? So that's why the curve itself will be unique. So solution for the equation will give you components of the curve. So from I to U, such that, okay, so it passes through the given point. So that gives you the smooth initial conditions. The second point, of course, is that it is integral. So did I write integral already? No, I didn't write integral. So I asked for integrality, so that the curve fits the vector field. That is, the velocity vector field of the curve will give you the tangent vector to the vector field at that given point on the curve. Yeah. So this is for every time t on the interval. And third, that okay. So this third one is a slight addition, if you wish. So the first two are the crucial ones, right? So you have an integral curve, but I will also include this as part of the theorem, as in the text. So we could do it as a separate result, but in a sense that this gamma is maximal. What does it mean? So if you have some other curve which is integral to x through the same point, is any other integral curve if eta is any other integral curve, to the vector field x uh, through the point P, through P. So that is eta of 0 is P. Yeah. Then I tilde is necessarily contained in I, and on I tilde these two coincide. So gamma of t is eta of t for all t in I tilde. So such a curve is called the maximal integral curve of x through p. So gamma is called maximal in the sense of this, right? So the domain of definition, so the maximality is with respect to the domain of definition under the inclusion relation. Yeah. So it's called maximal. It's called the maximal. Now, we can only say an integral curve, but once you take the maximal one, you do get. So let me just move this a little bit. Called the maximal integral curve of the vector field through the given point. So that is the theorem. Yeah. So direct consequence. I'll comment on the third part a little bit. So maximal integral curve. So in the following fashion, so if you use just uniqueness, existence and uniqueness, this is very local, right? So there is some interval and so on. So how do you get to something maximal? So I'll phrase this as an exercise. It's a nice little exercise, and this is where I pointed out at the beginning that the fact that we choose the intervals to be the domains of definitions of these curves actually matters. So let me phrase it in a concrete fashion. So how do I say this? If gamma and eta are integral curves, so you can deduce part 3 from part 1 and 2, right? So 1 and 2 directly follow from existence uniqueness for systems of ODEs with smooth initial conditions, and part 3 really follows from 1 and 2 in this following fashion via the exercise. So our integral curves of x as in the theorem of the vector field x such that now we have an additional assumption, right? So such that they coincide at a point. So gamma t naught is the same as eta t naught for some t. Then show that the curves are actually the same. So then show that gamma is equal to eta. So hint, as I said, use connectedness of I. So the typical use of connectedness that you would have seen in topology. Yeah? So you want to say something, two things coincide on an interval, you try to show the set you are interested in is both open and closed, right? So these are all smooth curves, so in particular continuous. So it's clear that the set of points where the curves coincide is closed, right? Because it's the inverse of the point 0. Now, if you can show that it is open, then you're done, right? Then by connectedness, it's the whole on the whole interval they coincide. So that's the exercise. Yeah. So nice little use of topology. Okay, so once you do this, then you see how to right. So then once you solve this exercise for me, then I will show you how to show 3 from 1 and 2. So let's quickly do this. So if gamma, just to distinguish the domains, I write I gamma for the domain to U, and eta from I eta to U are integral curves to a smooth vector field on U through the same point. So this is of course the crucial bit, because it tells you that the set of points where they coincide is non-empty, right? So at 0 they certainly coincide. Then the curve so then this exercise, so the exercise above gives us that gamma is equal to eta on I gamma intersection I eta, right? And this is non-empty because 0 is in there. This is non-empty as 0 belongs to it. That's the assumption of the curve passing through the same point, curves passing through the same point. So then what you can do, so these patch very well, right? From the intersection, these curves go on overlaps of the domains of definition, the curves coincide. Then you can define one big curve. So thus all these curves together, all such curves maybe. So all such curves, such meaning as above, right? Through the same point, to the same vector field, and so on. All such curves together form. So define maybe. So define an integral curve gamma p. Sorry. Where what is IP? Where IP is the union of all the I gammas as above, right? So you look at all integral curves to the vector field through the same point. So they may be in different, slightly different intervals defined for, but so you put them all together. And how do you define gamma p? Then, so gamma p, you just define by restriction on an I gamma is just okay, maybe I eta. So because I wrote this as gamma, so I eta is just eta. It's well defined. So the fact that on overlaps they coincide means that this is well defined. So this is called the maximal integral curve, and that's the gamma in the theorem. So this is the maximal integral curve that we were after. So I specify the point just so that fixing a point is what gives us maximality. So maximal integral curve through of x through p through p of x of the vector field x. Okay, so that's just a remark. Mm, Perhaps the following is also useful. I mean, I will not prove this for the moment, but let me just share a little lemma. I have a suspicion this might be useful when we go to surfaces. So, if need be, we'll look at the proof later, but I'll give this perhaps as an exercise. It's just an easy exercise, maybe two parts. Uh, Part one. Um, so, if so simple reparameterizations of integral curves are integral. So if gamma is an integral curve, so I'll write this in short form, meaning to the vector field through a point, etc. You have to take as understood. Then so is uh, t going to gamma t plus c for some constant c. So that of course t plus c is in the domain and so on, right? So that you have to always be careful because it may not be defined globally, but so you should take c small enough and fixed and so on. So but okay. So the second point is, so if you take the maximal integral curve, so if so maybe let gamma p be the maximal integral curve of vector field through a point. So maybe I should have written this also for the first part. And let Q be gamma P at some point. So you look at the maximal integral curve, go along the curve, take some point Q, which is reached at time S, yeah, because gamma P at 0 is P, right, by definition. So then show that. Okay, so maybe I should show that here. So then I'll simply write the statement. IP is merely S plus IQ. So it's a shift of the domain of definition by the translation, right? So you go along the integral curve for time S, and then you look at the maximal integral curve through that point. So, so that is gamma Q at t is simply gamma p at time s plus t. This is for all t in IQ, right? So what does this actually tell us? That if maximal integral curves, we saw that if integral curves meet at a point, then they coincide. This tells us that if maximal integral curves meet at a point, then they differ only in parameterization. So that is, if maximal integral curves meet at a point, then they differ only in parameterization. Of course, it also tells you that if you take a point on an integral curve and look at what the integral curve is, it is through that point. Then it is the same integral curve that you started out with, just after time required to reach the point that you are interested in, right? So, okay, so proof I will give it out as an exercise. Is something you should think about. There's nothing hard here, right? So you, it's just small observations. So the first part requires almost nothing. It's just definition of saying that IP is S plus IQ merely requires that uh, to look at what it means for some point to be in S plus IQ and so on, right? So in the domain of such a curve. So give your uh, sort of reparameterize your gamma q, call it something else, and then calculate it out. So of course, if there is time, I will do it as well. But perhaps now I should really move to surfaces. I think all that I wanted to say is marked here. Okay, we have to do examples for integral curves, right? Of course, so crucially, yeah. So we just didn't look at examples. So, okay, so let's do that. So I could make a few more remarks here, but uh, I will see how much time I have. Um, so examples. So we take the vector fields that it started out with. So the constant vector field, the identity vector field, and the rotation of vector field, and we see what the integral curves are, maximal integral curves are. So x of p was p comma 1 0. So it's the we fix the constant here for the map. So the maximal integral curve. So in these examples, it is also maximal because it will be defined for all time. So we don't have to worry about maximality. In general, it's somewhat more involved, right? So, but all these examples are nice. That gamma p of this vector field through a point p. So p will take to be arbitrary. So what is it? So it is just about solving this system of ODEs that we had, right? So you write out you start with a curve. You want to, so suppose that gamma is a curve from I to R2. So in this case, we could assume R to R2, which is what we will do. So then you look at the requirement that the velocity vector field at every point should give you the tangent vector through that point on the curve to the vector field. So that gives you a system of differential equations, ODEs. So I simply write out the system. So this is gamma 1, it's the first component. There are two components, it's an R2, right, for the curve. So at a point T naught. So what should this be? We use integrality. So this should be the first component of the function associated, the map associated to the vector field and through the curve at the point that we are interested in through the curve. So this is through the point gamma 1 T naught and gamma 2 T naught. So that is one equation. So here is another. So this is then the second component. So second component of the curve, you equate to the second component of the map associated to the vector field. Sorry, this is gamma 1, this is gamma 2. So this is for every T naught in R. So how do you solve this? So this is your this is sort of the easiest kind here. Because what is this? So maybe I should have written it there itself. So I will write it now, maybe in red, so that. So what is this? So the first component of along the curve, because the of the vector field is simply 1, because it's a constant vector field, right? So at any point p, x1 of p1, p2 is it's just 1. So the value the function the map takes is independent of the point. So while this is 0, so it is constant. So you solve the first equation. What do you get? So solving for the equations. We get. So this is all the easy exercises or examples that were done in your ODE courses. course at some point, maybe even in your UG or maybe in your MSc. So it's some constant, yeah. So gamma 2 is also some constant. Where K1, K2 are constants. So for example, the second equation tells you that, so the gamma 2 is independent of time. Yeah. So as does the first one. So just whatever it is, it's constant. So that's how we define the vector field. So it's not a surprise. Yeah. So now use the initial condition to determine what K1 and K2 are. So now gamma 1 of 0 is P1, gamma 2 of 0, sorry, is P2. And so this implies that K1 is P1, K2 is P2. So gamma P of T is P1 comma P2. This is just P. So it's a constant curve. Yeah. So the maximal integral curve for the constant vector field is the constant curve. Not surprising. Yeah. If it was anything else, we should be surprised. Okay, so then let's take the identity one. So this maybe I leave as a little exercise, because then you can go to the third example. So just I'll recall that, sorry, x of p is p comma p. This is the identity vector field. So calculate the maximal integral curve here. Through an arbitrary point P. Through P. Yeah, so a simple set of equations. Not that the next one is any harder, but it is certainly more appealing, pictorially at least. So the rotation vector field, what was this? So this is P. Well, maybe this I. Well, okay, this is okay. This is P. So if P1 and P2 are the components, maybe I write it down. So this should be minus P2, P1, right? Where P is P1, P2. So now, how do you calculate gamma p? So we look at, so this leads us to consider the differential equation system, ODE system. So there are just two here. So gamma 1 by gamma t at some t is, what is this? So minus gamma 2t. And here this is gamma 2 by gamma dt. This is gamma 1t. So of course, this again you have seen the general solution for this is right. It's very suggestive that of sines and cosines. So the general solution looks like gamma 1t is alpha cos t plus beta sin t. And the second one is alpha sin t minus beta cos t. Now, since it passes through the given point, so we can determine the constants. So the initial values will determine what these are. So since it passes through, it meaning the curve passes through the point P is P1, P2. What do we get? So we get that P1 is gamma 1 of 0, but this is alpha, right? So you just substitute 0 in the equation for gamma 1t, sine vanishes, cos pops out. So and P2 is gamma 2 of 0, and this is minus beta. So this leads us to the equation for the maximal integral curve to be P1 cos t minus P2 sine t, and then it becomes plus there. So P2 cos t plus P1 sine t. So that's the maximal integral. So this is for all time t. So that's the maximal integral curve. So again, I think there was a picture. So let me quickly check this. So yeah, no, not this one. No, I think I. Oh no, okay, not this again. So I wanted the flow. I see. There it is. Yeah, this one here. So integral curves are drawn out. Nicely drawn picture in the book. So you have to fix points and so on. So, but it's very indicative of what is happening. Yeah? So you have to fix. So I think they have done 1 0 1 1 and so on. So just to see this. Okay, so let's move on to vector fields on surfaces. So for which we will use very strongly what we know of vector fields on Rn open subsets of Rn plus 1. So without even recalling what it is, I'll simply say, okay, so S will be an n-dimensional surface in Rn plus 1. I think he called it something else, n surface maybe. But so we understand by this that there is a function, smooth function defined on some open subset of Rn plus 1, whose set of regular points this is. In other words, the gradient is, so this is f inverse of C for some C, so it's a level set. And such on this level set, the gradient vector field is non-vanishing. Yeah, so that's the, so it's a hypersurface sitting inside, smooth hypersurface sitting inside Rn plus 1. So what is a vector field on this? So formally it is very similar. So a vector field on a surface S is a map. And here I assume that you have seen what the tangent space is, but I'm sure you have. So it maps a point on the surface to a tangent vector. So this again I write as P xp inside the TPRn plus 1. So we already know what TPRn plus 1 is. So it's I mean, so that's the definition. So it's merely a map from your surface to the tangent bundle of Rn plus 1. So if you fix a point, you get the tangent space at that point. Yeah? So it maps every point P on the surface to the tangent space to Rn plus 1 at that surface. I mean, so at that point. Now, of course, this is called tangent vector field. So if this is tangential to the surface, so if at a point, at every point P, this xp actually lies in the tangent space to the surface at that point. So this holds for every point on the surface. then you call a vector field a tangent vector field. Because we are in this very specific setting of hypersurface, yeah. So where the dimension is n of the surface in Rn plus one. So there is sort of one direction which is free for us, and this will give us a normal vector field. So we call a vector field a normal vector field. So this is very specific to this setting, right? Because we are in a codimension one situation. So the dimension of the surface we are interested in is one less than the ambient space. So on S, if at a given point, every given point P, this lies in the orthogonal complement of the tangent space to the surface inside TPR n plus 1. Yeah? So this is for every P. When you say orthogonal complement, you have to say where. Yeah. So this is inside TPRn plus 1. That is given. Because you already saw that the gradient vector field is orthogonal to the tangent space, right? So probably it was even an equivalent definition for your tangent space as being the ortho complement of the gradient vector field at every point. So, okay, so now we have to make one remark, sort of an important remark. And if you're somewhat unfamiliar with this before, then maybe I'll remark a little bit on this tomorrow as well. So, because, okay, so what does it mean for a function defined on a subset which is not necessarily open inside Euclidean space to be differentiable, right? So now I'll simply say what it means. So it's defined in this fashion. So we'll restrict our attention to just surfaces. Of course, recall that these surfaces need not be open, right? So you could just take nice polynomial. So your f from Rn to R to be x1 squared plus x2 squared plus xn plus 1 squared minus 1, and the level set at 0 gives you the sphere. This is compact, so it's not open. Um, so typically, your surfaces you consider may not be open, and so we want to say when a function is actually smooth. So the map is smooth if and only if it extends to a smooth map in some open neighborhood. Yeah. So if and only if f extends, in fact, how, because smoothness is local, perhaps it is best to say, okay, so I'll take surface alone here. So this of course is a general definition. So okay, so let me say this as, yeah, okay, those are the same definitions. So extends to a smooth map, which we'll call f tilde, from some open set containing S to Rk. Where U is some open set in Rn plus 1 which contains the surface S. So if you think carefully, this is how you define derivatives on, let's say, closed intervals, right? So this one-sided derivative business that you write, you can show that is equivalent to this existence of a smooth extension to something open and with something which contains the given set. Yeah? So of course it's done pointwise. So right, so because differentiability is always at a point, so a function is smooth at a point if there is a neighborhood of the point where it extends uh, to a smooth function on that in a neighborhood. And then of course, but you can say it's the same here, because you can take all such neighborhoods you get around all the points. That will give you an open set containing the subset of Rn plus 1 that you started out with, and so you can write it out like this. Yeah, so, but this is of course the same as saying that component functions are smooth. Yeah, so but okay, so that I will, so maybe I'll simply rephrase this for vector fields. So a vector field X is smooth on on an n surface, as is written in the book, is smooth. Uh, so if and only if the associated function is smooth. Yeah. So X is C infinity, where what is X? X is given by this relation as before, and X is a function from S to the from the surface to Rn plus 1 for every P. This holds P in S, sorry. So every point in the on the surface. Okay, so maybe I put a comma instead of an and. I should write it in a separate order. So for not necessarily open things, you define smoothness by asking that they have smooth local extensions. So okay, so let's then look at the corresponding existence uniqueness theorem for surfaces. So that will be the result. So the idea is, the definition of smoothness suggests what we should do, right? Because a vector field is smooth on an n surface if the function associated to it is smooth, but the function associated to it is smooth if it is smooth on some open neighborhood of the surface in Rn plus 1. And for such things, we already know, for open subsets in Rn plus 1, we know existence uniqueness of maximal integral curves. So we use that in order to get this. Yeah? So that's why we spend time there, because this is then a consequence of that. And the definition of smoothness. So those two, if you put together, you simply get this result. So what is this theorem? This is the existence and uniqueness of maximal integral curves. For smooth vector fields on surfaces. But okay, so that will be too long. So what should be the statement here? So you're given an n surface, sorry, uniqueness of. So the statement is that, so suppose S is an n surface in Rn plus 1. X is a smooth vector field on S. P is a point on S. Then there exists an open interval around 0, an open interval I around 0, and the parametrized curve gamma from I to S. So you take a curve on the surface through the given point. So sorry. So through P. Recall that through P means gamma 0 is P. Just for the first few times, it's worth recalling this, such that Gamma is integral to the vector field. Or maybe I should write it as points. Yeah. So, okay, I started writing it like this. We will leave it like that. Is integral to the vector field integral to the, sorry, the vector field x. That is, what does integrality mean? That the velocity vector field of the curve at every point gives you the tangent vector determined by the vector field. So for all t. In fact, we can write the function. So for all t in I. Since we said maximal, so let me also write. So, and if eta from I tilde to s, just as before. So except that now the curves lie in the surface that you have at hand. So is any other, so this is the statement about maximality, right? So the unique maximal integral curve. So there is any other parametrized curve through the point and through the same point P and integral to the same vector field x, then they are the same. So is any other parameterized curve um, through the point P, so through P, which is integral to the given vector field, so which is integral to the vector field x, then I tilde is contained in I. The statement is as before for the Euclidean setting. Yeah. So, and on the smaller one, these curves coincide. In other words, gamma is an extension of eta. So, and gamma can be, so it's called the maximal integral curve. So now for the surface, yeah, gamma is called the maximal integral curve. Um, 2x through p, 2x to the vector field x through the point P. Okay. So as I said, the proof is just putting various things together, right? So essentially three ingredients in the proof, two which I already mentioned, and the other is of course definition of the surface. So X is a smooth vector field, it's given to us. So what does that mean? So is maybe I write it slightly, is a C infinity vector field. So what does this mean? On S, there is an open subset U, open in Rn plus 1, containing S as well. So maybe I should such that S is contained in U. And the smooth vector field x1 on U, such that this is an extension of that. What does it mean? If I restrict x1 to S, I get the vector field we started out with on the surface. So that's what you mean by saying x1 is an extension. The vector field x1 is an extension of the vector field x. Now, as I said, there are 3 points that we will use here. The first point is S is an n surface. So what is it that we want to show? So we want to choose things in such a way that okay, so how do we use the definition? As I said, we use the definition of the surface in the fact that the uh, what is it? The gradient vector field is normal to is orthogonal to the tangent space to the surface. So that's the, so let me write it out. So implies by definition there exists some open set or open subset V of Rn plus 1 and function f, smooth function f from B to Rn plus 1 C infinity, such that the gradient of this function, so such that of course the f s is a level surface, arising from f, and um, on the surface itself the gradient is non-vanishing. So now, right, so we have two open sets here, u which comes from the smoothness of the vector field on S, and v which comes from the definition of f of S, in the sense that it is the function whose level set S is at some point, and such that the gradient vector field, oh, I forgot to put the arrow here, it's a vector field, yeah, so is non-vanishing. Yeah. So what we do is we simply say, take the intersection. Of course, we have to go to a further smaller subset because you want the non-vanishing, right? So otherwise you could simply take u intersection v, but because you want to be on the surface, you want to demand additionally that things don't vanish, the gradient doesn't vanish at these points. So set w to be essentially points in u intersection v such that the gradient vector field is non-zero at these points. So the claim is that this is open in Rn plus 1. It's easy to see. I'll ask why, so that you think about why it is easy to see. So if it were just u intersection v, you see it, but sorry, it is non-zero. But this non-vanishing condition is an open condition. So how do you use that in order to show that W itself is open? Yeah. Of course, notice first that S is contained in W. So notice that so that's why we put this additional condition of non-vanishing gradient. So and that both the function f and the vector field x1 are defined there. And what was the notation x1, right? So and the vector field x1 and are defined on W. So essentially the idea is take the intersection, but ensure that S is contained in there, right? That's the relevant piece of information. So we ask for the non-vanishing gradient. Now this is again an idea which you have probably already seen, is you take the component of x1 along the gradient. So you define a vector field y on S by, so pretty much exactly what this is, the component of x1 along the gradient So this is what, so the inner product with the gradient is what gives you that component, and it's normalized. Yeah, so this is the scalar, and then of course times the gradient. So maybe I write the scalar here. So this is suitably normalized. So what is it normalized by? Of course, the norm of the gradient. So here is one place where we use the non-vanishing nature of the gradient. You can divide by its length. So times the gradient vector field, right? So everything else is is a scalar, and so so what is this? This is simply the uh, component of x1 along the gradient of f of the vector field x1 along. So okay. um, now we use the crucial observation that I mentioned above, is the gradient is orthogonal to the tangent space. So since the gradient vector field is orthogonal to the tangent space for every point at every point on the surface, we get that. um, and and since y, no, no, I mean, because of this, so I want to say something else. Uh, what do we have as a consequence? So the second term vanishes. So on the surface itself, y and x1 coincide, because the second term here, this vanishes, right? So the coefficient vanishes, and so that term vanishes in the vector field itself. So now the so what do we know? Okay, so y is a vector field on W. So for such things, we know maximal integral curves. Now we will claim that this maximal integral curve through the point P to the vector field y, actually it maps into the surface. So it's actually a curve on the surface itself, right? So by the definition of y. Yeah, so that's why we define y carefully. So sorry. So what we will have here is let gamma be the maximal integral curve. Sorry, this is not. This is W be the maximal integral curve. So now we are in the usual setting of W is open in Rn plus one. Yeah? So we know everything about such maximal integral curves. So integral curve for the vector field y through the point P. Now the key claim is that this curve actually lies in S. So and that will give us the vector field that we are looking for, right? So the maximal vector field on the surface. So why is this? So this is so. So here you have to recall your calculus. So because, so what we have to say that the image of the curve lies in the surface, we have to use the defining relations, right? So we have to say that the so f of gamma at t should be C, right? Because the S is a level surface of of constant C associated with F. So we want to say that f of gamma at t for every t in I is actually equal to C. So why is this so? So let's do the calculations for this. So maybe it is clearer if I say that. So then so that is, we need to show that um, gamma So f of gamma t is C for every t in I. So if we show this, we would have shown that the curve actually lies on the surface S. So how do we show that? So for that, we look at mm, the derivative of this, right? So this is d by dt at the point t. So what is the derivative of a curve? Of course, this is just a map now from I to R. It's just a real function, real valued function on the interval. So from several variable calculus, you know that this is given by the gradient at the point gamma t tested against the velocity vector field, right? So the inner product is the standard inner product here, the dot product. So everything sits inside Rn plus 1. So the dot product, there's only one inner product we are considering. But now we use the integrality of gamma to replace, so we leave the gradient as such. But by integrality of gamma, so the velocity vector field actually gives you the tangent vector at that point. So this is just y of gamma t, but this is 0, right? Why? So maybe that's let me put a y here so that you ponder about this. I mean, I'll say it is clear, but of course you have to tell me why it is clear. Yeah? So what does that give us? So this gives us that f of gamma, because it's on a connected set, is constant. So this is for every t, right? So in the interval on I. And so values at every point is the same. So f of gamma at t is f of gamma at 0. We know I always contains 0. But what is gamma of 0? This is p, and this is f of p. P is a point on the surface, so this is c. So this is why we've shown, and the claim follows. Right? So we've shown that the curve, integral curve to y at um, every point. I mean, so integral to y along the curve. So the maximal integral curve to y actually lies inside S. Yeah, so that's the thing, and the claim follows. So okay, so I'm over time. Um, so let me only say, okay, so we quickly say, so clearly and the velocity vector is actually x of gamma t. Yeah, the first one is pretty much by definition, but why is the second one? So because so gamma was initially the integral curve to y, but we already saw that on y, I mean on S, x and y coincide. In fact, x1 and y coincide, but then x1 and x also coincide. So y itself is x on the curve, and we have shown that on the surface, and we have shown that gamma lies in the surface. So this follows. Yeah. So maybe I write it down in. So since um, gamma maps into S, and on S, uh, y is x1 is x. So, so in fact, y is x is what we want here. So and maximality also follows from before. Yeah. So from the Euclidean setting. So that no separate particular argument we have to give. corresponding maximality in the Euclidean setting. Okay, so I will stop here. So we will have some little corollary of this, and then we'll talk a little bit about orientation first thing tomorrow before we move on to. I mean, so much of our lectures will be following this notion of vector fields and integral curves of vector fields. Yeah. Okay, so I'll stop here.